Yeah, building the freeway through the Sugarloaf mountain range is quite a complex task. It's not just one mountain, it's actually a series of mountains that flow from east to west, one after the other. The traditional way of building a freeway through there would have been cut and fill. You basically cut through the hill and you use that material to fill the valleys and the gullies, but some of those gullies are 50, 60 metres deep, so that wasn't an available option here, and we chose to build some viaducts, and a viaduct's really just a long bridge that spans across the gully, so we basically connected up each of those mountain tops. So as part of doing an alliance, the alliance design team have to finish a design that's initially prepared by Roads and Maritime, so that's given to them under the contract to carry out. For this project, the alliance team considered a number of ways of building the bridges. The two main options for a bridge of such size being incrementally launched, and that means you build the bridge from one end and sections come out. The other one's a balanced cantilever, where you start at each pier and the segments come out each side of it. For this project, the best option was a balanced cantilever bridge. It has a better set of spans to match the surrounding terrain, and it was the most cost-effective overall solution.
The viaduct bridges that the Alliance is building here are concrete box girder bridges on tall piers. They have main spans of 75 metres. This particular bridge behind us, Viaduct 3, has an overall length of about 200 metres. Because of the terrain in this area, a decision was made to precast as much of the concrete as we could. So in this case, the columns for the piers were made in precast sections, and then the deck also has been precast up on another part of the site and then brought down here to be assembled into the deck of the bridge. So it's what's called balanced cantilever construction for the superstructure or the deck of the bridge, and that's done by starting at the pier and then putting segments on, one on each side as we go to keep it balanced. So you put a pair on and then they're stressed on using steel cables, and then you just work your way out putting pairs of segments on as we go. When you get out to the half span length, you then move to the next pier and do the same thing again until it comes back and meets in the middle. On the end, there's also, in this particular case, there are 8 segments assembled from the abutment out towards the cantilever, and they're suspended from the truss until such time as we can attach them to the cantilever. Again, that's done with post-tensioning cables, steel cables. After that's all done, of course, we come through and put on the parapets and the railings, which then form the full deck that traffic will see. The launching gantry is a long steel truss, is 165 metres long. It's as long as 2 spans of the bridge. It contains about 1,000 tonnes of steelwork, and it's used basically as a crane to pick up segments and transport them out across the bridge site and to place them into position. The largest segments that we'll be transporting weigh 110 tonnes. It's capable of launching itself out from pier to pier, and later on will actually walk itself through the cuttings into the next bridge site.
What you can see behind me is the construction of the first section of the viaduct. There's twin viaducts in this area. They're about 200 odd metres long and about 36 metres above the floor of the gully. The next viaduct that we'll be constructing is Viaduct 2. Again, that's a twin bridges. That one's about 250 metres again. And the third viaduct we'll be constructing, Viaduct 1, is the longest. It's about 350 metres, and that's up to, I think, about 38, 39 metres above the floor of the gully.
There's lots of innovation we have in the viaducts. It starts all the way from the foundations all the way to the superstructure. We've also taken the innovation further for the columns. For the logistics of the area, we've come up with a solution of precast columns to make the erection quicker and safer. And also for the deck erection, we've chosen a precast segmental balanced cantilever solution that will speed up the construction and reduce the risk of working in this particular area.
This is the precast yard that the Alliance has established to cast concrete segments for the viaduct bridges. We've got 50 to 60 people working in the precast yard here, from steel fixers to concreters to carpenters that work on the forms, and the guys that handle the segments out here. In this precast yard, we take in the reinforcement that's been pre-bent from one steel. We assemble that up into cages ready for each segment. We then place the reinforcing cage in the mould. We then have a batch plant that produces concrete from around the corner here, and that's brought down and we cast the segment in the mould. It's then cured, brought out and stacked in the yard here to complete curing, ready to go down onto the job into the bridges. So this is producing under factory conditions, essentially, and so that gives us higher quality, better control of the process, gives us a higher turnaround and a faster production. So there's benefits for the Alliance and for the project as a whole. Also allows us to control the environment around us more. We're not moving from site to site producing things, it's all in the one place. Under the shed we've got our steel fabrication area and we've got the 5 moulds for production. So that's 2 for the column segments and 3 for deck segments. It's got 3 gantry cranes in the roof that can handle 15 tonnes each to assist us in moving things around. We've got the straddle carrier that picks up segments and transports them around the yard here, stacks them and then loads them onto the truck to go down to the bridge sites.
There was a number of key challenges as we got through the mountain range. The first is obviously the terrain and the topography. To be able to build any construction work, you need to be able to get plant and people in and out of the job safely. So we've had to build a number of access tracks in cooperation with the surrounding landowner to be able to get people in and out to do the work. I guess in addition to that, we've also faced the conditions of approval which require us to minimise our clearing, and that's a good outcome, and we've worked really hard to achieve that. By having the viaducts or long bridges, for example, we've been able to maintain a large amount of vegetation that would otherwise have been removed. In overcoming the challenges in the range, we've been able to maintain our clearing within the clearing limit by having very strict controls on what we do. So we have a permit system where we control what areas are cleared. We have a record keeping system where we pick up by survey all of the cleared areas, and we manage our work so that everybody's aware of where they can and can't be at any one point in time. So that creates a lot of effort and energy that goes into making sure that we do that right, and we have done that right to date, and as a result we're under our total clearing limit for the project.
All of the relative teams on the project have had their own challenges, and I guess they've the really pleasing thing from my perspective as the Alliance Manager is seeing those teams rise to the challenge.
This is a very exciting project from an engineering point of view. The types of construction you see here aren't done that very often in this country, and certainly not as many. This site has an enormous variety of difficult types of construction going on. So from that technical point of view, it's very exciting. It's very challenging from the environmental point of view to restrain our footprint and to work within restricted areas, and then to maintain the environment around us. But it's great to come to every day and see the progress that's being made.